Thank you for joining this panel discussion on setting the stage for energy storage needs and challenges in the transportation sector. My name is Thomas Kirchstetter, and I'll be moderating this conversation. I'm a senior scientist at Lawrence Berkeley National Lab, where I serve as the director for the Energy Analysis and Environmental Impacts Division. I'm also having a lot of fun serving as the Interim Division Director for our Cyclotron Road Lab Embedded Entrepreneur Program. I'm very honored to be joined here today by this very esteemed panel of leaders to have this conversation with you. So let me introduce our panelists. First, I'd like to introduce Yi Shui, who is the director of the Precourt Institute for Energy at Stanford University. And he's also a professor in photon science at the SLAC National Accelerator Laboratory. Yi is indeed a preeminent researcher on nanotechnologies for batteries and for other sustainability technologies. Also with us today is Rachael Nealer. Rachael is the Deputy Director for Transportation Technology and Policy at the White House Council on Environmental Quality, where she advises and coordinates on the execution of the administration's transportation priorities. Also, she's the Interim Deputy Director for the newly established Joint Office of Energy and Transportation, which is leading the development of the National EV Charging Infrastructure Plan. Also with us is Amol Phadke. Amol is a staff scientist in the Electricity Markets and Policy Department at Lawrence Berkeley National Lab. Amol is also the lead author of some very influential reports called the 2035 reports for short, which articulate decarbonization pathways in the power and transportation sectors. And last but certainly not least, Nina French, who is the technical director of the energy portfolio at the United States Department of Defense's Defense Innovation Unit. As the technical director, Nina plays a key role in leveraging advancements in energy and materials technologies in order to enhance capabilities and strengthen resilience across defense installations and distributed operations. So I want to thank each of you for being here with us this morning. So in this conversation, we'll have the opportunity to talk about battery R&D challenges and opportunities on the way to commercialization. We'll talk about charging infrastructure, security and safety concerns associated with a large-scale shift towards an electrified mobility future. And last, and certainly not least, we'll have an opportunity to talk about environmental justice and energy justice. So I'd like to also make a note to our audience members that throughout this conversation, you should feel free to type in the Q&A section of the chat function any of the questions that you'd also like to have us address. We'll have time for audience Q&A towards the end of this panel session. So I'd like to begin the conversation with battery R&D challenges and opportunities on the way to commercialization and ask the first question to E. So E, the first question to you is, electric vehicles are gaining in popularity and in market share, yet they make up only a small part of today's vehicle fleet. Now, just a few moments ago, we heard Shirley Menn speak about how far we've come on improving battery energy density, cycle life, safety, and we've achieved cost reductions as well. But I'd like to ask you, what are the key battery R&D challenges that we still need to overcome? What are the breakthroughs that are necessary in order to accelerate the pace of decarbonizing the transportation sector?
Well, thank you, Tom. I agree with Shirley. I think the challenges Shirley outlined, energy density, whether you can double or triple the energy density is important. Cycle life going from 3,000 to 10,000 or even 30,000 cycles. This could be very important. The cycle life and calendar life go together. Can you make, instead of 7 years, hey, let's go to 30 years lifetime. That doesn't mean for the car, you need it to be 30 years, right? Once the car retired, that battery pack still be useful for something else, maybe for the next car even, right? So that needs to be considered. This has a very important cost implication right there. And then Shirley talk about cost reduction. I completely agree. We need to get the cost lower from currently, let's see, $120 to $150 per kilowatt hour in the cell level, down to, can we go to $50? And that would be amazing. That reduces the cost of the car. This helps large deployment for the car. So in addition to this, let me mention a couple more just to resonate back, right? Safety surely talk about that, but let me emphasize that more. And safety is so important once you have cars everywhere, and the degree of safety. If the car parked right there, even without use, if something going wrong, whether it's doing charging or just sitting right there, just some internal reaction, you want to reduce the accident rate by a whole lot. We probably need to do 10 times better than the existing technology can offer. So we can even ask the question: can you make the batteries completely safe? Never catching fire or explosion. We can go deeper, Tom, if we have time later, right? We can go deeper about that. So I agree this is a big challenge. Let me also mention one more that's kind of related. I will call it as a scaling. How do you scale the battery production and also the circular economy of that, right? And the resources utilization. Well, if talk about billion car, we need to have running passenger car on the road, 50 kilowatt hour per car. We are talking about 50 terawatt hour of production right there. That's a lot of batteries right there. How do we even do the scaling? All the materials, all the tooling, how do you finance that? Where do you build it? And this whole series of issues needs to be considered. Scaling is not only just keep building it. This R&D behind it, right? I mean, what's the materials you choose? Where do you get the materials from? How do you refine it? How do you make it? And how do you do circular economy? This is highly related. And then I also added one more to be more specific. Can we develop the next generation of chemistry? The material is just so abundant, right? No cobalt, even no nickel, right there. I don't know, maybe even no lithium. I mean, lithium sounds necessary at this moment. People talk about sodium, this other type of chemistry. Can we do that to truly enable scaling? I think this requires R&D. I mean, for the time consideration, maybe I should just pause right now, and so we can talk about more.
Yeah, well, thanks very much for articulating a lot of the science and the research and development that we still need to accomplish in order to have wide-scale deployment of electric vehicles. And maybe we'll have time to come back to some of the material science questions, particularly around safety later on. Amol, let me ask you the next question, just to sort of go beyond a little bit R&D. I'd like to consider what are the mobility storage options that might fall between R&D and commercialization. And I know that you've considered a lot more than just vehicles. You've thought about off-road transportation modes. So, what are those things that we should be talking about in terms of decarbonizing the transportation sector?
Well, thanks, Tom, for that question, especially the off-road. It's my favorite thing to talk about.
Yes.
So off-road, I think we should basically consist of, aircrafts, trains, and ships. Now, aircrafts have a significant constraint on how much weight they can carry. I mean, these days, they don't even let you check in a one free bag. And of course, you need fundamental battery chemistry breakthroughs to achieve the energy densities required for aircrafts. That is not exactly true for ships and trains. The large iron ore carriers can carry weight equal to 2,000 aircrafts in one ship. So, and on trains, again, the energy density constraint is not so binding. And what is surprising is that trains in the US are still diesel electric, meaning that they are using an onboard diesel generator in this day and age to drive the electric motors of those trains. And what we find, given the dramatic battery technology improvements, that it's now economical to add a rail car full of batteries to get rid of that diesel consumption. And battery energy density is not a constraint. Now, for ships, such opportunities exist for example, short to medium distance ships. But for long distance ships, the battery chemistry can look a bit different because they can be a little bulkier. They don't require this ultra fast charging and discharging requirements. And they could also accept a little lower cycle life. That means that you could have access to chemistries which are much cheaper, such as iron air batteries, which can really kind of dramatically change the shipping industry. And more importantly, why should we care about these modes? Ships and trains are highly efficient, but from an air pollution perspective, they are very damaging. So for example, shipping contributes to about 250,000 premature deaths every year from their air pollution. And that air pollution tends to disproportionately affect disadvantaged communities. So from that perspective, because there are interesting technology and commercial options available, we really have to kind of focus our attention on these non-road applications from an environmental justice perspective. And we can discuss a lot more, but I'll stop here.
Yeah, thanks, Amol. So I early in your response, I had the image of everybody having a battery in the carry-on bag to help the plane get there. I think we'll need a different solution, of course. But Nina, can I ask you the next question, please? And I'd like to hear from you your thoughts about how the defense industry or the Department of Defense can play a role in commercializing and maybe catalyzing wide-scale transportation decarbonization. And then just because one of the themes of the day is about partnerships to accelerate the pace of decarbonization, maybe in your answer, you can speak a bit about how DoD can partner with the national labs or academia and industry to help achieve this goal.
Yeah, so the Defense Innovation Unit was stood up about 5 years ago by Ash Carter, the current Secretary of Defense. And the idea was to tap into the commercial sector and do the reverse of what we did in the national labs of tech transfer and bring commercial technologies into the government. And so we are focused on prototyping. We're not a funding agency, but we broker with DoD to bring commercial technologies rapidly into DoD. So I think there are places that we can do that very effectively. We have programs right now in my portfolio that work on battery standardization. Joe Bryan mentioned yesterday that the Navy alone has 5,000 different types of batteries. So it's hard for DoD to compete with the EV market because we don't have a big enough market to bear. But I think that we can work on standardization so we can tap into that commercial market and bring that into DoD. We have a program on battery recycling, which we heard a little bit about yesterday. And we'll, again, really, there are companies out there that are doing this. We will tap into that. And then we have advanced batteries that we're looking at that more than just lithium ion. Mm-hmm. Would love to work with you a little bit on that and what he's doing with battery chemistry and Amol. I think that there is a really good market here for DoD to kind of bring technologies forward. We don't create a huge market like Tesla does or like EVs in general do, but we can do a lot to reduce the risk of commercialization by bringing in our needs, both operational, which is anything that moves in the DoD, and installations, which is the bases. There are over 400 bases across the world. And there are so many opportunities there. We're looking at sustainable aviation fuels. So the aircraft part of transportation, I think, is really interesting and important. And Amol and I have talked a little bit about trains and what we could do with trains for, he just has some brilliant ideas about trains to come in for disaster relief packed with batteries. Mm-hmm. And DoD is very committed to that. So Defense Innovation Unit, I think, really important and really can I think lead the way in some of these issues, especially things that are higher risk.
Yeah, thank you. And
Tom.
Amol, we'll get your reflections on some of that in just a bit. But let me ask Rachael, and in fact, let's pivot just a touch away from batteries to charging and charging infrastructure. As we know, batteries won't get this there alone. We'll need a lot of charging infrastructure, and the joint DOE-DOT office, which is developing a national charging infrastructure plan, that's going to help shape how $5 billion are spent to deploy electric vehicle charging infrastructure is created across the United States. So maybe speaking about that, Rachael, what do you think are the biggest challenges to deploying EV charging infrastructure at such a massive scale?
Yeah, thanks, Tom. We have a big task ahead of us. And I'd actually like to point out that the good news is that we're not starting from scratch. To kind of take a look at the technology analogy, Professor Shui and Professor Meng also talked about the technology progress we've made. So we've done a lot on batteries, we've done a lot on charging over the last couple decades. And so very similarly on the deployment side, we're not starting from scratch. We're just building on the great work that's already been done across the Department of Transportation and the Department of Energy. Our Clean Cities coalitions are a great example of that in the Department of Energy. Alternative fuel corridors, which are the priority for the initial build out of the EV national charging network on the DOT side, the Federal Highways Administration has actually done 5 previous rounds of designating alternative fuel corridors. So the great news is that we're not starting from scratch. We have some of these networks already in place. The challenge will be the scaling up component. And so the Joint Office is really the functional means to provide the support for that scaling up. So what I think is really great about how the bipartisan infrastructure law was written was that you have these major investments. You have $7.5 billion in EV charging over 5 years as administered by the Federal Highways Administration. You have $5 billion set aside for the Federal Transit Administration to electrify transit. And then you have $5 billion for the Environmental Protection Agency to electrify school buses. And we know from historical experience that that's a lot of money going through the government. And these programs are really set up to fund the transit agencies, these school districts, and the states. But a missing component in the past has been this technical assistance and this really key piece of providing support to all of those projects to pull together what will be a national EV charging network that is convenient, reliable, and equitable. And so really the Joint Office is there to help pull all of those different components together, provide the resources both proactively and reactively. And the Joint Office itself is kind of based on this whole of government approach, bringing together 2 agencies to make to really achieve a greater good. But how I really see it as we start implementing the EV charging network is that this really needs to be a whole of stakeholder effort. And so we need people from the utilities, from the charging manufacturers, from the labs, from all the agencies, from school districts, transit agencies. There's just the state DOTs, the state energy offices. There are just so many people and such great work already happening in these areas that we really need to pull it together and synthesize it, provide a vision. And for the Joint Office, that vision is a future where everyone can ride and drive electric. So I think that's our challenge is putting all of those things together. We have a lot to accomplish in 5 years. And I'd also just say one more thing. So the scale up of that deployment is going to be a challenge, but I think we're up for it. The other thing is that our infrastructure, our EV charging network today isn't the same as it was 5 years ago. And so we're also going to have this added challenge of deploying the technologies that are ready and commercial today, but also taking into consideration the innovation and the evolution of these technologies. So by the end of the 5 years, we don't have a 2020 EV charging infrastructure. We have a future-proof EV infrastructure.
Right on. I think that's a great point. And also thank you for hitting on sort of the partnerships that are needed to come together. I think that's very consistent with today's theme as well. Let's go back just briefly, maybe talk a little bit about technology for charging infrastructure. And maybe the question is to you, E. Do you think that wireless charging technologies or extreme fast charging of vehicles, that technology, are they going to be at the ready in order for wide-scale deployment, in order to have a significant role in accelerating the pace towards transportation decarbonization?
Yeah, Tom, this is excellent questions. So we actually talk about this, discuss about this a lot at Stanford. We have our Storage X initiative. Indeed, one of the important areas, maybe let me mention fast charging first and then go to the wireless charging. So fast charging, if you look at the fast charging, what are the potential problems? One is the batteries problem, whether batteries can take it or not. The second is actually your charging station, your cable, how much power you will need, right? So let me touch upon the batteries fast charging problem. Indeed, in DOE, this Department of Energy has the Excel program, extreme fast charging. There's a team of scientists from national lab, get together to look at this problem. There's a lot of progress made. If we define extreme fast charging as 15 minutes to 80%, right? There's different definitions. But let me just use 15 minutes to 80% of the capacity. Once you do fast charging, you start to play out lithium metal dendrite on the graphite anode side. When your cathode might have a little bit of damage as well, whether your electrolyte have high enough ionic conductivity to handle that. So within DOE, this is a full-scale program. We look at this. I would say there's a lot of progress made. I can see it's possible down the road to do so. Let me also differentiate to be the different chemistry. Lithium iron phosphate versus MMC, they're different. Lithium iron phosphate can handle more of the fast charging on the cathode side. But the anode side, if you have graphite right there, right, it becomes harder. You can plate out lithium. I would say we are not far away. I wouldn't call it, wide-scale deployment. I think we need to do some pilot scale. We don't need every car, right? All the charging stations to do that. Yeah, we need some. Pair with the right chemistry to do it, the right battery design to do it. This is absolutely necessary. I will be strongly supportive of that. Let me also mention the new chemistry coming up, like silicon as an anode. These can enable fast charging very different from graphite. That's why this problem is couple R&D problem is as silicon as anode coming in, you increase the energy density by a lot. Mm-hmm. At the same time, you can have fast charging, the technology I involved a little bit, I invented the silicon nanowire anode. I saw some of the data, right? It's 5 minutes, actually 6 minutes charging to 80% possible. I mean, that's just incredible. But of course, that's not ready yet to deploy in a larger scale. I'm telling you what's possible right there. So, and then fast charging also have the charging station consideration. If you think about 100 kilowatt hour battery pack in the car, you do 10 minutes, right? Fast charge. My God, that's what 600 kilowatt of power pumping out. If you do even faster, you can see 1 megawatt of power pumping out. It's like driving an airplane already. The power coming out to that scale, really to that scale, right? So it's like airplane power type of scale. Your cable, can you handle that, the cooling? And this needs to come together. So to that extreme, maybe we are not quite ready yet for large scale deployment. Some pilot demonstration is fine. Now, wireless charging over the past decade, MIT group, actually Stanford has a group, my colleague Xianghui Fan also showing it's possible within half a meters by wireless power transfer, with decent efficiency, 90%, 95%. I think doing pilot scale, we are there, but large scale deployment, hey, let's see. Are you going to use wireless charging when the car parked right there? That's one application. I mean, the crazy application will be during driving on the road, keep doing the wireless charging. You kind of have wireless, charging right on the road. I mean, that is whole infrastructure thinking, right? I don't think we are ready to do so, but parking the car, stay right there, perhaps pilot scale demonstration already.
Mm-hmm.
I think it's ready, right? I mean, the whole economy needs to be understood better. So I'll pause right here for now.
Yeah, thanks, E. And you mentioned dendrites, which of course touches on a safety issue, and you're referring to charging and grid infrastructure, basically. So let's switch gears just a bit and maybe talk a little bit more about security. Nina, maybe the question to you. I think you might have a valuable perspective on this. What do you think the most significant security risks are that we face in a highly electrified mobility future? And then if you would, what do you think we need to do to sort of minimize those safety risks?
So we think about electrification in two ways. We think about on the battlefield, anything that moves, where we have a big program right now on hybrid vehicle electrification for tactical vehicles, light, medium, and heavy, everything from Humvees to tanks. And part of that is the security issue of not transporting fuel, which is where so much of DoD risk comes from. In terms of the US, I think that base installation electrification is important, but I think it's more of operations that we're focused on in DoD. Look at what's happening right now in Europe. If they had charging stations and at least hybridization, we would be in a much better position. So I think from a national security point, that it's very clear that we're going to go to 100% electric vehicles at some point. But in the meantime, what we're going to do is hybridize to extend range of tactical vehicles and also to make the whole stop idle is what kind of started this generation in DoD. So we have no heat signature. We can sit at idle, with which we call hotel loads. And these vehicles go out for 8 hours at a time, and we can reduce fuel consumption. But I think there's a much bigger picture that we're trying to get to, which is full electric. But as we've all been talking about, you have to have charging stations, you have to have batteries that can accept the charges. There's an operational complexity here that's very important.
Thanks, Nina. So I want to ask Amol you one question that I'm pretty sure you'd like to speak to, but I also want to move a little bit quickly because I want to get to environmental justice before our time is up. So Amol, can you talk about opportunities for sharing storage assets and perhaps what that might do to help reduce security risks and resiliency for the grid?
Yeah, I think this question is important today. It's going to become more important in the future as we move everything or nearly everything to be electric. That electric grid resilience is of utmost importance. So you're thinking, what are some of the other backup options that can be deployed at scale? So for example, the US has one of the world's largest rail network. Now, if you have battery electric rail, which is kind of being retrofitted for diesel, in emergency times, you could deploy these battery electric locomotives or battery rail cars to locations which are experiencing emergency events. And that scale of storage is very large. So we believe there is a potential to deploy 200 gigawatt hours of storage on wheels just to kind of electrify rail. Now, the recent California blackout, we were 5 gigawatt hours short. So we're not talking about small chunks of storage and here and there that can be deployed. Similar opportunities exist for ships, but we do believe that everywhere in the world there's extensive rail network. We need to, and this is just one idea, we really have to think hard on how we're going to kind of back up the grid which we believe is going to kind of power our energy sector.
Mm-hmm. Great. Thanks, Amol. Okay, so Shirley Meng mentioned a number of grand challenges and accomplishments around energy density and cost and cycle life and safety. We're talking about needs for charging infrastructure, and we've talked about scale up, both the batteries and infrastructure for charging. Yesterday, we heard Secretary Granholm say that energy and environmental justice was one of the administration's guiding stars. And so, Rachael, I'd like to ask you this question about energy and environmental justice. So with regards to investments in EV charging infrastructure, what's needed to ensure that all communities are going to benefit?
Thanks, Tom. That's a really great question, and something that we've been spending a lot of time thinking about as we've been designing the program. So we are ensuring that Justice 40 initiative, the president's initiative, that 40% of the benefits of the investments go to disadvantaged communities. We're ensuring that that applies to the EV charging programs. And that's an umbrella application. So that's the EV charging formula program, the competitive grants, transit electrification and school bus electrification. And so transit and school bus, you could probably see a little bit of how that might benefit disadvantaged communities. However, we're working really hard to make sure that as the EV charging network gets deployed, it's being deployed in an equitable way. And so one way that we have decided to do or decided to design the program is ensuring that community engagement is actually an eligible cost for the funds. And so really making sure that we're building into these decisions, even though the money is flowing to the state DOTs, they have the ability to go to communities, talk with them about their EV charging plans and hear from the communities on whether they want them. Because one of the things that became very apparent in our early stakeholder engagement was that just because you place an EV charger in a disadvantaged location, a disadvantaged community, doesn't necessarily mean that the benefits are for that disadvantaged community. So we really want to make sure that we're providing complete support. There are probably some localized air quality benefits for that, but we're thinking more holistically about how EV charging will benefit disadvantaged communities, not just the location. And I think that really starts at the ground floor with talking to communities on a very local basis about what their needs are.
Yeah, that's fantastic. And honestly, I feel like we can have an entire panel session on energy and environmental justice if we'd like to, but thanks for that response. Let me turn real quick to one or two audience questions, and we'll see if we can hit them before we run out of time here in just a few minutes. So real quick, will batteries face the limit like Moore's law in electronics? What's the prospect of future batteries?
Yeah, we often compare this Moore's law for batteries. Battery doesn't have the Moore's law right here. The runway, in the energy density is several times right there. The voltage has been about 5 watts. So I would say there's no equivalent Moore's law for the batteries, unfortunately. You're lucky to have 6 to 8% improvement every year for the batteries, right? But I will consider batteries in a different way but it's challenging of maybe we need to think about certain law in terms of scaling. That scaling is just gigantic. That's a big issue right there. Not in terms of size, not in terms of energy density, right? Moore's law is about the size of transistor, how many transistors you can pack. We don't have the energy density Moore's law right here. But scaling is something we need to think deeper.
Thanks, E. Yeah, agreed. So it looks like we only have a couple of moments left. So rather than trying to field another question to squeak in and running out of time, let me just pause and thank each of you for joining me this morning and having this really interesting and informative panel discussion. So thanks for your time. I really appreciate it. And it's great to see all of you.
Thank you.
Thank you very much.
And then to the audience, please be sure to go back to the program tab to move on to the next portion of the summit, and be well.
Thank you.